Ionic compound stability hinges on lattice enthalpy, not merely the octet rule. Understanding lattice formation enthalpy is crucial for assessing ionic compound stability. Lattice enthalpy measures energy to separate ionic solids into gaseous ions. For NaCl, 788 kJ mol 1 is required, highlighting the balance of attractive and repulsive forces. Calculating lattice enthalpy involves three-dimensional crystal geometry, surpassing mere force interactions. Additional crystal structural factors are essential for accurate calculations. Bond length is the equilibrium distance between bonded atom nuclei, measurable via spectroscopy, X-ray, and electron diffraction. Each atom contributes to bond length. In covalent bonds, each atom's contribution to bond length is its covalent radius, half the distance between two similar atoms in a covalently bonded molecule. Bond length calculation uses the formula R is equal to Ra plus Rb, where R is the bond length, and Ra, Rb are covalent radii of atoms A and B. Van der Waals radius represents an atom's size, including the valence shell in non-bonded situations. It's half the distance between similar atoms in separate molecules. Different bond types have specific covalent bond lengths, like OH 96 pm and CN 116 pm, reflecting variations in atomic interactions. Common molecules exhibit varying bond lengths, such as H2 74 pm and I2 267 pm, illustrating differences in atomic bonding distances. Bond angle is the angle between orbitals containing bonding electron pairs around a central atom, determined by spectroscopic methods, indicating molecular shape. Bond enthalpy is the energy to break a mole of bonds in a gaseous state, expressed in kJ mol 1, like HH bond enthalpy at 435.8 kJ mol 1. Bond enthalpy varies with bond types, with O2 having 498 kJ mol 1 and N2 at 946 kJ mol 1, indicating stronger bonds with higher enthalpy. Heteronuclear molecules like HCl have complex bond strength measurements, with HCl bond enthalpy at 431.0 kJ mol 1, varying in polyatomic molecules. In water, the first OH bond requires 502 kJ mol 1, while the second needs 427 kJ mol 1, highlighting changes in chemical environment. Average bond enthalpy accounts for energy differences in polyatomic molecules, calculated by dividing total dissociation enthalpy by bonds broken, like in water. Bond order: the number of bonds between atoms is 1 in H to 2 in O2 and 3 in N2, indicating stronger bonds with higher bond order. Isoelectronic molecules share bond orders. F2 and O2 have bond order 1, while N2 CO and NO plus have bond order 3, affecting stability. Single Lewis structures often fail for molecules like ozone, with experimental parameters needing resonance structures for accurate representation of bond lengths. Resonance uses canonical structures for molecules like O3, where single Lewis structures are inadequate, forming a hybrid that accurately represents the molecule.